Before this semester, I bought a $10 mug with the claim that it would keep heat in a liquid significantly longer than this 50-cent cup. Today, I'm asking a simple question. Did I get screwed? The only reasonable thing to do is to run an experiment. So I filled both cups with hot water and a thermometer. I took a reading every minute, an experience I would not recommend to anyone else, and recorded the liquid's temperature until it was stable. After taking a look at the raw data, it already seems apparent that the mug did make a significant difference. But let's take a closer look. First, I subtracted room temperature from each data value to put both functions in terms of degrees above room temperature. The temperature of the room was slightly different between experiments, so this makes for a cleaner comparison. Now let's turn the raw data into equations we can compare. For this, we can use Newton's law of cooling, which is written in variable form y equals c e to the kt plus z. We are looking for the value of k in each equation. This number compares the amount of time it takes for each liquid to cool a certain amount. Before we can do this, though, we have to solve for some other constants. First, we assume the added constant d to be equal to 0, since the liquid's temperature approaches room temperature, and we are measuring degrees above room temperature. This means our function should approach 0, and d controls the value of the function as time approaches infinity. Next, we need to find a 0 point to plug in for the coefficient of our exponential. Unfortunately, it's impractical to measure at 0, so instead, I will choose the time of 2 minutes as a 0 point. This is where the thermometer's reading was maximal, meaning it was where our measurement was reflective of the internal temperature for the first time. Plugging in the values from each equation, we have y equals 108 e to the kt, and y equals 114 e to the kt. Now, in order to find the value for k for each equation, we have to plug in another point. I chose the value of 10 minutes after the 0 point for each equation. Plugging in each value, we get 80 is equal to 108 e to the 10k, and 96 is equal to 114 e to the 10k. Our k value for our plastic cup is approximately negative 0.03. Our k value for our metal mug is approximately negative 0.017. The difference in k value is going to just describe the length of time the heat is retained by the liquid. So when contained in the metal mug, the heat will last for twice as long as it would in the plastic cup. Let's check this against our data values with this graph right here. As you can see, the line 50 degrees above room temperature is denoted, and we can clearly see that the time it takes for the plastic cup to cool to 50 degrees above room temperature is around 30 minutes, while the metal mug takes almost an hour. We can also plug in other values to test this theory, and they are equally reflective of similar results. Now we can compare the shape of the curves created by the equations to the shape of the data curves. We see strong correlation, which means what we can draw from the equations will likely strongly relate to the data curves. Thus we can conclude that the metal mug keeps liquid at about twice the heat of the plastic cup at any given time. This seems well worth a $10 investment to keep my coffee warm while I sip on it and study. Thanks for listening, and cheers!